Hello, everyone, and welcome back to the lecture series on chemical equilibrium and the relative strengths of acids and bases. You have probably heard of sulfur, which is the starting point in the manufacture of sulfuric acid, the most commonly produced chemical in the world. Sulfuric acid is used in the manufacture of fertilizers, synthetic fibers, mineral extraction, batteries, cleaning agents, detergents, paper production, and the manufacture of paints and dyes, to name just a few applications. It is classified as a strong acid, which has a very specific meaning, as we will see in this lecture. It should not surprise you to learn that the chemistry of an aqueous solution often depends critically on pH. Therefore, it is important to examine how pH relates to acid and base concentrations. We will begin our discussion with the simplest cases involving strong acids and strong bases. You probably remember that strong acids and strong bases are strong electrolytes, existing in aqueous solutions entirely as ions. While there are many different acids, relatively few qualify as strong acids. Also, remember that although sulfuric acid has two ionizable protons, only the first ionization is complete. It is a good idea to commit the short list of strong acids to memory. Since the ionization of a strong acid is complete, the concentration of hydronium ions at equilibrium will be equal to the initial concentration of the strong acid. For example, if we prepare a 0.1 molar solution of hydrochloric acid, the concentration of hydronium ions in the solution will be 0.1 moles per liter. All the hydrochloric acid ionizes, and no hydrogen chloride molecules remain. Thus, at equilibrium, when the ionization is complete, the concentration of hydrogen chloride will be 0, and the concentrations of hydronium and chloride ions will each be equal to 0.1 molar. Therefore, the pH of the solution at room temperature will be the negative base 10 logarithm of 0.1, which equals 1. This is a very low pH, consistent with a relatively concentrated solution of a strong acid. In general, solutions of two different strong acids having the same concentration will also have the same pH, as strong acids dissociate completely. Now, let's examine what happens in the solutions of strong bases. The most common soluble strong bases are the ionic hydroxides of the alkali metals, such as sodium hydroxide and potassium hydroxide, and the ionic hydroxides of the heavier alkaline earth metals, such as strontium hydroxide. These compounds completely dissociate into ions in aqueous solution. In other words, a solution labeled 0.1 molar sodium hydroxide consists of 0.1 moles of sodium and hydroxide ions per liter of water. In this solution, there will essentially be no undissociated sodium hydroxide. Although all alkali metal hydroxides are strong electrolytes, rubidium hydroxide and cesium hydroxide are not commonly encountered in the laboratory because they are quite expensive due to the scarcity of rubidium and cesium. The hydroxides of the heavier alkaline earth metals are also strong electrolytes. However, they have limited solubility and are used only when high solubility is not critical for a given task. What you should remember here is that solutions of two different strong bases having the same concentration will also have the same pH, as strong bases dissociate completely. Acids and bases are common both in nature and in the laboratory, and most of them are classified as weak. They influence our daily lives in countless ways. Not only are they present in our foods, but acids and bases are also crucial components of living systems, such as the amino acids used to synthesize proteins and the nucleic acids that encode genetic information. Weak acids like citric acid and ascorbic acid, also known as vitamin C, give citrus fruits their characteristic tangy, sour taste. Citric acid and another weak acid called malic acids are among several acids involved in the Krebs cycle, which is used to generate energy in aerobic organisms. In general, the application of acid-base chemistry has played critical roles in shaping modern society, including industrial manufacturing, the development of advanced pharmaceuticals, and many aspects of environmental science. Weak acids ionize only to a limited extent when dissolved in water. At equilibrium, an aqueous solution of a weak acid contains a mixture of unionized acid molecules, hydronium ions, and the corresponding conjugate base. The degree to which a weak acid ionizes depends on the structure and concentration of the acid, as well as the equilibrium constant for the ionization. Now, consider the ionization of a weak monoprotic acid, represented as HA. The equilibrium expression for this reaction can be written as shown below, where Ka is the equilibrium constant for the reaction. More specifically, Ka is called the acid ionization constant. Although all weak acids ionize less than 100%, they vary in strength. The magnitude of the acid ionization constant indicates the strength of a weak acid. A larger ionization constant value indicates a stronger acid, whereas a smaller ionization constant value indicates a weaker acid. For example, acetic acid and hydrofluoric acid are both weak acids, but hydrofluoric acid is stronger, as evidenced by its larger acid ionization constant. In other words, solutions of equal concentration of the two acids do not have the same pH. Compared to acetic acid, the pH of a hydrofluoric acid solution will be lower. This table shows the structural formulas, conjugate bases, and acid ionization constant values for several weak acids. Many weak acids are organic compounds composed entirely of carbon, hydrogen, and oxygen atoms. These compounds typically contain hydrogen atoms bonded to both carbon and oxygen atoms. In almost all cases, the hydrogen atoms bonded to carbon do not ionize in water. Instead, the acidic behavior of these compounds is primarily due to the hydrogen atoms attached to oxygen atoms. Diprotic and polyprotic acids undergo successive ionizations, losing one proton at a time. Each ionization has an associated acid ionization constant. For diprotic acid, these constants are designated as Ka1 and Ka2. A separate equilibrium expression is written for each ionization, meaning two or more equilibrium expressions may be required to calculate the concentrations of species in solution at equilibrium. This process can be illustrated using carbonic acid, which is a diprotic acid. Note that the conjugate base formed in the first ionization acts as the acid in the second ionization. The following table shows the ionization constants of several diprotic and polyprotic acids. For any given acid, the first ionization constant is significantly larger than the second, and so on. This trend is logical because it is easier to remove a proton from a neutral species than from a negatively charged one. Similarly, it is easier to remove a proton from a species with a single negative charge than from one with a double negative charge. Dead tissue breaks down through chemical degradation and bacterial action. The latter often results in the release of volatile amines, such as cadaverine and putrescine. These amines are weak bases, and as their names suggest, the decomposition process is accompanied by a bad smell. Just as most acids are weak, most bases are also weak. The ionization of a weak base is incomplete and can be analyzed in the same way as the ionization of a weak acid. The ionization of a weak base can be represented by the equation shown here, where B is the weak base and Hb+ is its conjugate acid. Accordingly, the equilibrium expression for the ionization can be written as shown below, with Kb representing the equilibrium constant, specifically known as the base ionization constant. Like weak acids, weak bases vary in strength. The magnitude of the base ionization constant indicates the strength of a weak base. A larger base ionization constant value corresponds to a stronger base, while a smaller base ionization constant value corresponds to a weaker base. The following table lists several common weak bases and their ionization constants. Note that the ability of these substances to act as bases arises from the lone pair of electrons on the nitrogen atom. This lone pair allows the compound to accept a proton, which is what makes it a Bronsted base. On the instance of a weak base methylamine, this process is schematically represented here. At the beginning of this module, you were introduced to the concept of conjugate acids and conjugate bases. Here, we will briefly examine the properties of conjugate acids and bases, independent of their parent compounds. When a strong acid, such as hydrogen chloride, dissolves in water, it ionizes completely because its conjugate base, the chloride ion, has essentially no affinity for hydronium ions in the solution. Since the chloride ion lacks this affinity, it does not act as a Bronsted base in water. For example, you may have noticed that when a chloride salt, such as sodium chloride, dissolves in water, the chloride ions in solution do not accept protons from water to regenerate hydrogen chloride. The chloride ion, which is the conjugate base of a strong acid, is an example of a weak conjugate base. Now consider the case of a weak acid. When hydrogen fluoride dissolves in water, ionization occurs only to a limited extent because the conjugate base of the acid, the fluoride ion, has a strong affinity for hydronium ions. As a result, the equilibrium lies far to the left. Since the fluoride ion has a strong affinity for hydronium ions, it acts as a Bronsted base in water. If we dissolve a fluoride salt, such as sodium fluoride, in water, the fluoride ions in solution will, to some extent, accept protons from water. The fluoride ion, being the conjugate base of a weak acid, is an example of a strong conjugate base. Conversely, a strong base has a weak conjugate acid, and a weak base has a strong conjugate acid. For example, water is the weak conjugate acid of the strong base hydroxide ion, while the ammonium ion is the strong conjugate acid of the weak base ammonia. When an ammonium salt dissolves in water, the ammonium ions donate protons to water molecules, at least to some extent. In general, there is a reciprocal relationship between the strength of an acid or base and the strength of its conjugate, which is illustrated in this figure. To sum up, in this lecture, you have learned about strong acids, which ionize completely in aqueous solution. The number of strong acids is limited, and you should memorize their formulas and names. We also briefly discussed strong bases, which include the group 1A and the heaviest group, 2A hydroxides. Then, we moved on to the major group of acids, weak acids, which ionize only partially. We can use the acid ionization constant, denoted as Ka, to verify the extent to which a weak acid ionizes. We also briefly touched upon diprotic and polyprotic acids, which have more than one proton to donate. These acids undergo stepwise ionizations, with each ionization having a K value associated with it. In most cases, only the first ionization of an acid needs to be considered to determine pH. Like weak acids, weak bases also ionize only partially. The base ionization constant, denoted as Kb, is the equilibrium constant that indicates the extent to which a weak base ionizes. You already know that the conjugate base of a weak acid is a strong base, meaning it can slowly react with water. Conversely, the conjugate acid of a strong base is a weak acid, meaning it does not react with water. In the next lecture, you will learn how to predict the relative strength of an acid based solely on an analysis of its molecular structure. Thank you for your attention.